Alright, so today I'll be talking about learning mixtures of linear regressions in sub-exponential time via Fourier moments. This is joint work with Jerry Lee and GAUSSIAN. So the problem I'll be discussing has the distinction of being fairly easy to state and being fairly natural even to someone who might not think about learning theory all the time, so I'll dive straight into definitions. At a high level, this problem is about solving jumbled collections of many linear systems simultaneously. So suppose you have some solution vectors, w1 through wk, in d dimensions, and we're given linear equations of the following form. For every index L from 1 to n, I'm given a pair xl, yl, such that there exists some index I, possibly depending on L, for which wi inner product x sub L is equal to y sub L. Crucially, we're not given this index function IL, but we'd still like to recover the true solutions w1 through wk. Right, this is a fairly natural problem. What's known about its complexity? So even in the special case where you're promised that a unique solution exists, so the corresponding linear systems associated to w1 and wk are all non-degenerate, turns out that finding the true solution w1 through wk can be as hard as subset sum, even in the case when k equals 2. Okay, but in the face of this kind of worst case hardness, as learning theorists, it's natural to ask if there are settings where, under average case assumptions, we can get efficient algorithms. In particular, what happens if you make distributional assumptions on how the equations are generated? And so the most natural set of distributions to work with would be Gaussian ones. So now, in addition to these unknown vectors w1 through wk, let me also attach mixing weights, lambda1 through lambda k, which you can think of as generating some kind of multinomial distribution over the index set 1 through k. Now my linear equations are each generated as follows. For any index L, I'm going to sample x sub L independently from a Gaussian distribution, and in this work I'm just going to specialize to the case of isotropic standard Gaussian d dimensions. Okay, now for each L, I'm going to sample some index I with probability according to the mixing weight lambda I. Okay. And at the end of the day, I'm going to get as my response y sub L equals the inner product of wi and x sub L. And as before, the goal is to recover the w1 through wk. So this problem currently is already quite interesting, but you can actually add some additional complexity to the problem by asking what happens if my responses y sub L are corrupted with some white noise. So let's say now these y sub L's get an additional variance sigma squared perturbation, in which case now I'd like to recover the true solutions w1 through wk up to some error. And in this setting, we'll need some additional identifiability assumptions. So in particular, I'm going to assume that the solution vectors, w1 through wk, are actually pairwise delta separated in Euclidean norm. Okay. But it turns out that even in the case where sigma equals 0, so the noiseless case, this kind of question is already quite technically challenging. And in this talk, I'll talk about both settings, both the noiseless and the noisy. So this general model is often called a mixture of linear regressions, or MLR for short. And it was introduced by DeVoe in '89 and Jordan Jacobs in '94, and it's been studied quite extensively in the ML theory community for being a particularly simple but expressive example of a discriminative latent variable model. Okay, but one could ask, having seen this for the first time, what is the practical motivation of such a model? And as a theorist, one might ask whether, what are the theoretical motivations for studying such a generative model? Okay, so I'll answer those, both of those questions in the next 2 slides, starting with the practical motivation. So MLRs turn out to be an important special case of a more general generative model called a mixture of experts. This is quite popular in ensemble learning methods and is an essential component in various successful recurrent neural network architectures. Think gated recurrent units, attention mechanism, etc. Okay, and so from a theoretical standpoint, it's a very compelling question to understand the empirical successes of these architectures by developing a theory of learnability for these basic units, these so-called mixtures of experts. So what is a mixture of experts? It takes in as input a vector x and comes with, as the name suggests, a collection of experts, each of whom has a particular model. In this case, we'll specialize to experts which are equipped with linear models. And in addition, a mixture of experts has a gating network. This gating network can be thought of as some kind of random variable, potentially depending on the input x, which picks out one of the experts' responses and takes that to be the output for y. So typically in these applications, the point of having multiple experts and this gating network is so that for different parts of the domain, the gating network will select out the expert which performs best on that part of the domain. But it turns out that even for gating networks which are oblivious to x, this is already a very challenging question from the learning theoretic standpoint. Okay? So mixtures of linear regressions correspond to gating networks where you just have a multinomial random variable specified by the mixing weights, and this is totally independent of x. And as we'll see, it's already quite difficult to get learning guarantees for this distribution. Okay, from a theoretical standpoint, another reason why one might care is that mixtures of linear regressions are a pretty nice example of a mixture model, and mixture models in general have received a lot of attention in the theoretical community in recent years. So to recall, a mixture model is just a convex combination of structured distributions. This could be Gaussians, rankings, product measures, etc. And they've been popular because they're a very compact way of representing heterogeneity in your data. And on the technique side, it's a very elegant testbed for understanding basic learning primitives like clustering, distribution learning, and its robust variance, alternating minimization, information computation gaps, etc. Given a mixture model, there are a variety of different learning goals, but the one that we'll be focused on is the following. Given IID samples from your mixture, you'd like to recover the exact parameters of the components, as opposed to, say, doing proper density estimation. Okay, so so the goal that I gave for mixture of linear regressions was specifically given IID samples of the form xi, yi, I would like to recover the parameters, namely the mixing weights and the solution vectors, w sub I. Okay, so that's the goal moving forward. Okay, so now let's say a bit about what's known in this line of work on MLRs. So the techniques can broadly be categorized into sort of three buckets. The first is results that use tensor decomposition. Right? So this is a technique that's proven useful for other latent variable models as well. The one drawback about this technique is that in order for your algorithms to get polynomial time guarantees, you need to make additional strong non-degeneracy assumptions, typically some kind of condition number bound. And as a result, if you don't make such assumptions, a priori, your algorithms are still going to need, at best, exponential in k running time. Okay. On the other hand, there's another line of work from the sum squares literature on the problem of list decodable regression. So I won't go into details about what this model is. It's a much more challenging model to work with. And here the best results are algorithms that scale roughly as d to some large polynomial in k in the exponent. And finally, the work that's most relevant to this work is that of Li and Liang, who gave an algorithm that they called moment descent, which achieves sort of the best sample complexity one could hope for, in that it runs nearly linear in the ambient dimension and logarithmically in 1/epsilon. The only drawback is that, again, it incurs this extra 2 to the k factor. Okay, so the natural question to ask is there any algorithm that can circumvent this x of k barrier for learning mixtures of linear regressions? Now, there's a lot of compelling evidence that this x of k barrier is, in some sense, unavoidable. If we look at the corresponding problem of learning a general mixture of Gaussians, of which MLR is a special case, there's actually a lot of strong evidence that you can't do better than x of k. All right, so first of all, Moitra and Valiant in their paper showed that sample complexity that's exponential in k is necessary even in one dimension. And then interestingly, Diaconi-Colas et al. Showed that even for instances where the sample complexity, information theoretically, is polynomial, you need computationally exp of k statistical queries in order to learn this mixture of Gaussians. Okay. And recently, very nice work of Bruna, Regev, Song, and Tang showed that improving upon d to the k for these Diaconicus et al. Style lower bound instances would actually allow one to solve lattice problems. Okay, so this is pretty compelling evidence that you can't go below exp of k for general mixtures of Gaussians. And at a high level, how these lower bounds work is by exhibiting pairs or families of mixtures of Gaussians which match on all low degree moments. And while MLRs are a very specialized case of mixtures of Gaussians, it turns out that they enjoy this property as well. So there exists infinitely many pairs of MLRs whose degree k moments are actually identical. Now, this already gives, in some sense, a no-go theorem for any algorithm that only interacts with the data in terms of low-order polynomial statistics. And in particular, all existing algorithms that get global convergence guarantees for MLRs are based on that sort of paradigm. More speculatively, there is this low-degree heuristic that comes from sort of the sum of squares literature that would suggest that given that you have this moment matching example, that exp of k really is the right answer for learning MLRs. Okay, so now what do we show? We show that perhaps surprisingly you can circumvent this exp of k barrier by going just slightly beyond the method of moments paradigm. So first, in the noiseless case, we show that you can achieve the same kind of sample complexity guarantee as Li and Liang, but you can improve the dependence on k from 2 to the k to 2 to the root k. And correspondingly, in the noisy case, we can't hope for linear convergence, but we can still get very good error in using samples scaling subexponentially in k as well for modest levels of white noise. So some remarks. Of course, this manages to circumvent the exp of k barrier by going beyond just polynomial statistics, as we'll see. Notably, theorem 2 is also the first non-SOS result to handle the noisy case. And there are some other additional results in this paper that I won't mention, but I encourage you to check out the paper on the archive. Okay, so now let me say a bit about techniques, starting with a brief overview of how Li and Liang achieve their sample complexity guarantees. Okay, so how does the Li and Liang algorithm work? At a high level, what they do is try to learn one component at a time, and then essentially peel that component off from the rest of the mixture and recurse on the remaining mixture. So how do you learn one component of your mixture of linear regressions? Their algorithm, which is called moment descent, proceeds as follows. First of all, it's straightforward to recover the span of the regressors in this setting. So we'll assume, without loss of generality for now, that the ambient dimension is actually at most the number of components in the mixture. So their algorithm is going to maintain a guess for one of the solution vectors w at every time step, and it'll update this guess as follows. It's going to sample polynomially many random unit vectors, v1 through vm, and try to walk along each of those directions. If walking in one of those directions makes sufficient progress, suitably defined, then simply update your guess by keeping that direction that you obtained, by walking in that direction. Okay, so we update, and then the question is, what is this progress measure that we need to evaluate? Their progress measure is just going to be the squared Euclidean distance between your current guess and the closest true solution w sub I. Now, of course, we don't actually have access to the w sub i's, and so there's no way for us to exactly evaluate this progress measure. And so one of the key subroutines of this moment descent procedure is the way to approximate the progress measure. So the nice observation they make is that if I look at the distribution over residuals with respect to w hat t, specifically if I sample x comma y from my mixture of linear regressions and compute this quantity, it's distributed as a univariate mixture of Gaussians. And particularly the variances of the components of this univariate mixture are exactly the quantities I want. Namely, these squared Euclidean distances between my guess and each of the true solutions. And so the idea is, let me just learn this univariate mixture of Gaussians using the algorithm of Morchman invariant and output the min variance of my estimator. and that's going to be a proxy for the progress measure. The only issue with this is that the univariate procedure in moiture invariant requires method of moments, and as a result needs exponential in k time. So that's the key bottleneck in this moment descent procedure. And it is this part of the algorithm that we'll seek to improve to get our theorem 1. So how do we do this? So it's clear that the main sort of subproblem that you need to solve is the following. Given IID draws from just a univariate mixture of Gaussians, each with mean 0, I would like to identify the minimum variance of any one of the components. Okay, and so we already saw that one way to do this is literally just to learn the full mixture and then spit out the minimum variance of the, our estimator. So how do I do better? The first idea is that if I wanted to estimate the max variance instead, this is actually quite easy. It turns out that if you can, if you want to 1 plus alpha approximate this max variance, then all you need to do is go out to degree roughly k to the 1 over alpha. And correspondingly, you'll need samples roughly exp of k to the 1 over alpha. Okay, so the second idea is that how do I go from max variance to min variance? Well, the key idea is that the Fourier transform of a univariate mixture of zero mean Gaussians is another mixture of zero mean Gaussians. Namely, you take the variances of the original mixture and you take the reciprocals. And up to normalization, this is the Fourier transform. Okay, so now it becomes clear how to estimate the min variance. I compute the max variance of the Fourier transform, and then I take the reciprocal. Okay, and that's essentially our algorithm. So what you do is you compute an appropriate improper density estimate, d tilde, for this univariate mixture. And then it turns out that the way that we construct this density estimate, it's possible to exactly evaluate higher moments of its Fourier transform. And altogether, this gives us our estimator. Okay, so going back to the algorithm of V and Liang, where do we actually get the sub-exponential improvement? It turns out the main win comes from step 1. So step 1 here, I didn't mention exactly what capital M was in Li and Liang, but suffice it to say that it was some polynomial in all parameters. And so a natural question to ask is, if I use slightly more than polynomial, can I do some kind of balancing now that I have this min variance oracle? So let's suppose that I try not polynomially many directions, but exp of k to the 1 minus 2c directions, where c is some constant to be optimized later. Now the point is, if I try that many directions, with high probability one of those directions is guaranteed to be quite correlated with whichever true solution w sub I I'm currently closest to. And you can show that if I walk along that particular direction, then I'm going to make multiplicative progress roughly 1 minus k to the negative 2c. Okay, you can see this from the fact that this is roughly just 1 minus the inner product squared. And the point is that I can evaluate progress to within 1 plus alpha multiplicative error in samples roughly exp of k to the alpha. Here alpha is k to the negative 2c, and so in particular I'll need roughly k to the 2c samples. Okay, so now we're basically done. If I take c to be 1/4, then I only need to try roughly exp of root k directions, and I only need to take samples roughly k to the root k in order to estimate my progress. And that's roughly where the exp of root k comes from. Okay, so that's basically it for how to learn one component in the noiseless setting. And it turns out that in the noisy case, learning a single component this way still works quite well. But at least in the noiseless case, now you can go from learning one component to learning all components as follows. You can use this moment descent procedure that I've just described to get a warm start on one component, in the sense that I want to obtain some W, which is pretty close to a true W, but by pretty close, I mean an error that isn't dependent on the target accuracy. I can then take this pretty good estimate and boost it to arbitrarily good accuracy by using existing local convergence guarantees that are based on SGD on some natural loss function. And then the idea is that once I've boosted to arbitrary accuracy, I can just look at all points in my data set which have low residual with respect to this estimator that I produced, and just remove them from the data set. And the point is that after this peeling procedure, I have essentially removed almost all of that particular component from my data, and now I'm left with a mixture of k minus 1 linear regressions that I can then recurse on. Okay, so clearly in the noisy case, when we have white noise, this last step is no good. In particular, even if I had a perfect estimate for one of the components w's, I won't be able to remove all the points from that component because points from that component might have large residual just because of the white noise. What can I do instead? Well, I can try to more delicately analyze the dynamics of moment descent. And one of the sort of most technically challenging results in this work is to show the following statement, that if I initialize my moment descent to a guess which is somewhat closer to one component than the others, then if I run moment descent to completion, I'm going to stay closest to that particular component for all time with decent probability. Now the question is, how do I ensure that my initial guess is significantly closer to one component than the other? I won't go into details about how this initialization works, but suffice it to say that if you do this in a careful way, then by combining steps 1 and 2, we get our algorithm. Namely, if I run moment descent a bunch of times, randomly initialized each time, then every component is going to sort of show up in one of those runs. Namely, for one of those runs, I'm going to start off closest to that particular component, and then if I run moment descent for that iteration, I'm going to end up with a good estimate for that component. Okay, so I'll just repeat this many times. I'll pick up all the components eventually, and that's my algorithm. Okay, so that's all I wanted to say about technical details. So now let me just move on to open questions. So clearly the most pressing question is to understand what the right dependence on k is, given that it's not x of k. And this work is just sort of like a first stab at that. It would be very surprising if the answer were actually x over root k, so I conjecture that it's probably much closer to poly k. I think another interesting question is to understand this noise tolerance much better. So right now we require noise which is much smaller than the pairwise separation. So recall we needed something like delta over poly k white noise. And it could be that for much larger levels of noise, something beyond this sort of tracking-based proof that we use for the noisy case could work. More ambitiously, so this is still part of this program of trying to understand learnability from mixtures of experts. So I think the two immediate steps following this work are as follows. One, we could try to understand more sophisticated classes of experts. So you can imagine experts that aren't just a single linear model, but which have an additional activation, like a sigmoid. Right? So this would correspond to essentially a mixture of generalized linear models, and it would be very interesting to understand learnability for this family of mixtures. And then additionally, so this would be sort of a departure from the sort of mixture model literature in that, so right now we're working with gating networks that are oblivious to x, and that's why we can think of this as just, given by some family of mixing weights, lambda 1 through lambda k. If the gating network actually depends on x, so perhaps it selects experts depending on what part of the domain the input x falls under, essentially nothing is known in this sort of generality. And so I think that would also be an interesting technical question for future study. And finally, when I started this work, and we noticed that this Fourier approach was useful, it was quite a surprise because it sort of flew in the face of the intuition we had developed regarding the low degree heuristic. So I think it would be very interesting to see whether this Fourier paradigm has other uses in distribution learning. Yeah, so those are the open questions. I encourage you to ask me any questions in the comments or during the synchronous session of the stock conference. But for now, yeah, that's all I have. So yeah, thanks for listening.